Welcome to the lecture series in Organic Chemistry Unit 2, which is dealing with the organic reaction mechanism. This is the second episode in continuation to the first one, where we dealt with some of the basic concepts. In this episode, we would be talking and extending a little of our previous episode, where we talked about the reagents and the nucleophile and electrophiles. So, nucleophiles are very important in organic reactions. We would extend it to their stability and the factors affecting thereof. And also we would learn about the types of reactions which are generally present for organic reactions. So, for this particular episode, we plan to start with the reactivity of nucleophiles, the factors affecting their reactivity, and the types of organic reactions, which are substitution, addition, elimination, rearrangement, and oxidation and reduction types. We would be talking about these reactions in detail and would cite an example each for each type. You would recall the characteristics of nucleophiles. Nucleophiles are nucleus loving, which means that they are electron rich and they always are seeking electron deficient centers. And they are very crucial for all types of organic reactions, because on the basis of these nucleophiles we are categorizing the reactions as nucleophilic or electrophilic, substitutions or additions, and many other. So, it is very important to talk about what affects the reactivity of nucleophiles. There are a number of factors which affect their reactivity, and there are interrelated terms like basicity and nucleophilicity, which determine their stability and their nature. There are two more factors which affect their reactivity: inductive effect and resonance. And we start with a term called basicity. You are familiar with the bases and the acids, and generally the bases are related to their basicity. Their strength is determined in terms of basicity, and similarly the acidity of acids tells about their strength. And how do we define basicity is the ability to accept a proton, or also the other way of defining is in terms of donating an electron. If you would recall, when we were defining nucleophiles, we said that nucleophiles are the ones which will go for an electron deficient center but not a proton. Here is where we differentiate between a base and a nucleophile. So, basicity is for the base which accepts a proton, like this amino group, which takes a proton and gets converted into ion. It has taken up one proton, and we generally define the strength of bases on the basis of their pKb values. Lower the value of pKb, higher is the basicity. The rate of reaction in case of bases is defined by Kb, which in turn ascertains the value of pKb, and lower the value of pKb, higher is its basicity. So, to see how does basicity vary in case of amines whom we consider as highly basic, let us take the example of alkyl amines, wherein we have one alkyl group, two alkyl groups, or 3 alkyl groups. You know that the amine with 3 alkyl groups is called as a tertiary amine, the one with 2 is called a secondary, and the one with 1 is called as a primary amine. As you can see, all of these amines substituted or partly substituted have an electron pair on the nitrogen atom, which can be donated to the species which will be electron deficient. What will decide the basicity of these amines? Which will be more basic? The expected order is tertiary, which will be more basic than secondary, which will be more basic than primary. What does that mean? That means the tertiary amine, which has 3 alkyl groups, will be able to donate its pair of electron the most easily. Why? I think it can be rationalized in terms of the 3 R groups which are present on the nitrogen, an electron donating effect, and help in facilitating the release of this particular lone pair. However, in the case of secondary, we have only 2 alkyl groups which are facilitating the donation of this lone pair, and in case of primary, we have only 1 alkyl group. So, we can say that tertiary will be the one which will be able to donate its pair of electron most easily. But what do we see when we are changing the solvents? What do we observe is in non-aqueous solution, that is a solution where you do not have water in the system and some other organic solvent is there, the basicity of these amines varies in this order, tertiary being the most basic, secondary being the second, and primary being the last, which was the expected strength also. But what happens in case of aqueous solutions? You know that aqueous solutions means we have water in the system. There the same sequence of basicity does not remain. What happens is secondary becomes the most basic, which is more basic than primary, and then the tertiary. That means tertiary becomes the least basic. How do we rationalize this order of basicity? There are 2 reasons for this kind of an order of basicity. One is solvation. Solvation in aqueous solution is due to the presence of water molecules which are able to solvate the amine, and the other one is steric crowding in tertiary amines. These 2 factors are differently playing their role. Solvation is trying to stabilize the amine which has minimum number of alkyl groups. As a result, the tertiary becomes the least basic, and in case of the second factor where steric crowding is present in tertiary amines, if we look into the previous slide, we know that there are 3 alkyl groups. Now, these alkyl groups make it difficult for nitrogen atom, the lone pair, to get solvated or let the solvent molecules solvate this particular molecule. As a result, the lone pair becomes less available for the substrate to be acted on, and therefore, the order of basicity as shown here. If we compare an aromatic and an aliphatic amine, what do we observe? Which one will be more basic? Let us try to rationalize. We have pyridine as the aromatic amine and we have trialkyl amine as the aliphatic amine. Both the nitrogens have their lone pair with the molecules, but what is the difference? That in the case of pyridine, we have nitrogen which is sp2 hybridized. There is a double bond here. So, this is sp2 hybridized, whereas this nitrogen being saturated has sp3 hybridization. And you would recall from your basics in organic chemistry that an sp2 hybridized atom or a group is more electronegative as compared to the one which is sp3 hybridized. So, sp3 hybridized group here is less electronegative. What do we conclude from this? That more electronegative means it is able to hold its electron pair to itself and not let it go to the other substrate. So, it becomes less basic. Whereas in case of aliphatic amines, this being less electronegative, let the electron pair present on the nitrogen go to the substrate and becomes more basic. So, we can say that an aliphatic amine is more basic as compared to an aromatic amine like pyridine. An important term in the context of nucleophiles is nucleophilicity. There is no doubt that the nucleophilic character of a nucleophile decides the nucleophilicity. But in the previous episode also we mentioned that nucleophilicity and basicity are two very interrelated and quite confusing terms. How the two are different? Well, nucleophilicity is the ability to react with the substrate and form a bond with the electrophile. So, please remember that the nucleophile will always form a bond with carbon and not with hydrogen. Of course, it expresses the relative strength of nucleophiles and also depends upon a number of factors like availability of electron density, which is very obvious. Until and unless it has a good electron density on itself, it is not able to act like a nucleophile. Polarizability, which is related to the size of the atom. Larger the size, more polarizable the atom is and more nucleophilic in turn. Also, it depends upon the nature of the solvent, as we saw in case of amines when we were talking about the order of basicity. So, these are the factors which decide on the nucleophilicity, as we shall see in a few examples to come. Strong base is a strong nucleophile if the attacking atom is the same. We are using the terms base and nucleophile interchangeably, but you have to always remember the basic difference between the two. Now, if the attacking atom is the same, in these examples we have oxygen as the attacking atom, be it hydroxide ion or water. In both the cases, oxygen is the attacking atom. So, if both of these are same, then the strong base means the one which is able to accept a proton easily will be a stronger nucleophile also. And we know that it is much easier for hydroxide ion to accept a proton and get converted into a more stable molecule of water. As a result, water, which is not that keen to accept a proton and give hydronium ion H3O plus, as a result the nucleophilicity of hydroxide is greater than that of water. So, when we consider the size of the atom, we see that larger the size, more nucleophilic the atom is. For example, in the first case, we have SH minus and OH minus. We have the attacking species sulfur and oxygen. Sulfur being larger in size has a better polarizability and therefore is more nucleophilic as compared to the hydroxide ion. Similarly, if we consider their neutral counterparts, that is the thiol and the alcohol, we find that the thiol is again more nucleophilic as compared to the alcohol. Most crucial comparison between nucleophilicity and basicity. Let's take a few examples wherein we find a reverse order of these two factors. So, if we take fluoride minus alkoxide or amine and RCH2 minus, what do we observe? We see that in this case, the order of basicity is fluoride is the most basic, then RO minus, then amine, and lastly the alkyl or the carbanion group, whereas the nucleophilicity has the reverse order, that is RCH2 minus being the most nucleophilic, and then amine, then RO minus, and fluoride ion has the minimum nucleophilicity. The reason being the same what we've seen in the previous slides, that is the ability to accept the proton in case of fluoride is the maximum, and then of course it is the minimum in case of carbanion. Therefore, fluoride becomes the most basic and the alkyl negative ion becomes the most nucleophilic. Similarly, if we consider the halogen group atoms, their ions, what do we observe is that I minus is the one which is least basic and it is the most nucleophilic. We can rationalize it again in the terms of a number of factors which we talked in the previous slide, that is first of all their ability to accept the proton, their polarizability, the size, and of course other factors are also there, but then here on the basis of these factors we see I minus is the most nucleophilic, whereas F minus is the least nucleophilic. The second factor which affects nucleophilicity or the nature of nucleophile is the inductive effect. We defined inductive effect earlier also. Inductive effect is defined as the induction of polarity in a bond. And what is special about inductive effect, that it operates through sigma bond. There is no involvement of the pi bond, and that is how it differs from resonance also. It is a permanent effect, and if we see this example, what do we observe? In this alkyl halide which has a chain of alkyl groups and then a fluoride at the end, fluoride being highly electronegative tries to pull electrons to itself, making the adjacent carbon slightly positive. And this effect does not remain till the next atom to the electronegative atom, rather it extends further and goes on to the third and the fourth. But do remember that it is generally observed up to the second carbon atom very well. By the time it comes to the fourth carbon, the effect diminishes. It's quite obvious that in the vicinity of this atom, whichever group is there is the one which is most effective. In this case, we call it as minus I effect. Why? Because here the electronegative atom is attracting electrons towards itself. Now, we take another case where we have an electropositive atom like lithium attached to the alkyl chain. Here what is happening is lithium, being electropositive in nature, tries to push electrons towards carbon and making the adjacent carbon with a slight negative charge. We call this as a positive I effect or a plus inductive effect, because the electropositive atom is pushing electrons and making the carbon partly negatively charged. This effect, similar to the minus I effect, diminishes by the time it reaches the fourth carbon atom, is observed the maximum in the second carbon atom. The third effect which affects the nucleophilicity of nucleophiles is called as resonance. Resonance is also called as mesomeric effect, and this, in contrast to the inductive effect, is due to delocalization of pi electrons. As we shall see in this example, we have a butadiene molecule. Here this double bond moves towards the single bond, and in turn, to stabilize the bonds, the double bond next to this single bond moves to the CH2 atom at the end. You would recall here the use of curved arrows. This is the arrow which shows the movement of bonds or the movement of electrons or the movement of an electron pair. You would recall from your previous episode. This is in resonance to then the leading species which has a positive charge because the bond from here has moved to the next one, and this one, by virtue of the bond moving on to this CH2, it makes it negative, this becomes positive, and the order can be the other way round, wherein we have a positive charge on this carbon and negative on the other one. The structures which are shown through resonance can be again of course depicted like this, wherein we represent the upper bonds by a dash bond and the lower ones, the single bonds, are of course remaining as such. The bonds which are labile, which are moving from one to the other, are shown by a dash bond, and this is what depicts a resonance structure of this particular molecule. All the contributing structures are called as the resonating structures, and we call this phenomenon as resonance. Now, let us see how does resonance actually affect the nucleophilicity of the molecule. We have an example of an alkynyl chloride where the delocalization is involving a lone pair also. There is a double bond and there is a lone pair on Cl atom which is participating in the delocalization. Here you can see the curved arrow shows the movement of an electron pair. In turn, this bond moves to the CH2 group, and what we get as a result of this is a positive charge on chloride and a negative charge on the terminal carbon atom. So, this is what again is showing the resonance structure, and this is what we rationalize for the nucleophilicity of the two amines here. One is aniline, another is cyclohexylamine. Here you can observe that aniline has a lone pair on the nitrogen of the amine group which is participating in the delocalization of the electrons. The lone pair moves inside, as a result the bond in the benzene molecule moves on the next one, and so forth. You can see that this lone pair is getting involved with the double bonds of the benzene ring. As a result, there are a number of resonating structures which are developed because this lone pair is participating in the delocalization process or in the formation of resonating structures. We can say that this lone pair becomes less available for the donation. What do we infer by this? It means that the aniline molecule will have that lone pair less easily available as compared to the cyclohexylamine, which does not have a delocalization of this kind available. So, this is how what will happen is the cyclohexylamine will become more nucleophilic as compared to aniline, and this is how resonance will affect the basicity or the nucleophilicity of the amines. We have one more kind of nucleophiles which we call as ambident nucleophiles. These are the nucleophiles which can attack a substrate through two possible sites. An example for this is cyanide, which can attack through a carbon as well as through nitrogen. Similar to the cyanide ion, we have nitrite ion which can attack through oxygen as well as through nitrogen. Here are the two resonating structures for the nitrite ion. So, we call such species as ambident nucleophiles. This was as far as the reagents, specifically nucleophiles, were concerned. Nucleophiles and nucleophilicity is an important concept in establishing a reaction mechanism. Therefore, we should keep all the points in mind. Well, with the reagents over, we come on to the types of reactions which generally organic molecules undergo. What are the various types of reactions which we encounter with organic molecules are substitution, addition, elimination, rearrangement, and oxidation and reduction. The substitution reactions are the ones, the name also suggests, here one group or atom gets substituted by the other group or atom, whereas in case of addition reactions, there is addition to a double or a triple bond. In elimination reactions, we have elimination of a small molecule like water or any other molecule which gets eliminated during the course of a reaction. Rearrangement reactions are very important in organic chemistry. There are number of rearrangements which are known by the names of the various scientists who have discovered the reactions. So, all those rearrangement reactions will be dealt in rearrangement types of reactions. Oxidation and reduction reactions, though not very specific for organic molecules, but in general all types of reactions can be carrying out or may be carrying out a kind of oxidation or reduction. When we get into the details of oxidation and reduction, we would realize how does the oxidation or a reduction state get changed during the change of reactant to products in case of organic reactions. So, all these types of organic reactions which we have mentioned now will be dealt in the next episode of our lecture series, and it is time to sum up. So, what have we seen in this particular presentation? Mainly was about the nucleophiles, their strength, the basis on which the reactivity of nucleophiles depends, the difference between nucleophilicity and basicity, and the factors which are affecting the reactivity of a nucleophile, like the size of the atom, the polarizability, electron density of the molecule, and also the solvent system, which becomes a deciding factor at times for the strength of the basicity or the nucleophilicity of the nucleophiles. We have also given a brief introduction of the types of reactions which generally the organic molecules or the substrates undergo, which included the substitution, addition, elimination, rearrangement, oxidation and reduction reactions, about which we will study in details in our next episode.